You are probably wondering about the possible real-life applications of differential equations. This video will help you gain understanding about its various applications, especially in the aspect of a mixture flow problem. Come and join us.
In mathematics, differential equation is an equation that relates one or more unknown functions and their derivatives.
Among the many applications of differential equations is modeling a continuous event.
The specific example that you may encounter in classroom is the mixture flow problem.
That refers to a chemical solution that is continuously added to another mixture and may be poured out at the same time.
Perfect example that we can witness at home would be a brine solution. It is a homogeneous mixture that composed of two substances, water and salt.
One common use is to season or preserve food. Depending on the cooking application, brine may reach salt concentration up to 20%.
Prior proceeding to solving the real-life applications of a mixture flow problem, here's what we need to remember first.
A theory may be complicated, but with practice, it becomes relatively easy.
The concentration of a substance inside a container, which we denote as dC over dt, is equal to the input rate minus the output rate, where both the input and output rate are solved by multiplying the concentration and its flow rate. We also need to remember that the concentration of the output rate is dependent to that of the input rate. This is because the concentration of the input rate gets mixed with the substance inside the container. Hence, constantly changes the concentration that comes out of it with respect to time. Now that we have our formula, we can now show a typical example of a continuous mixing situations in differential equations. We recommend to understand the principle behind this because all the sample problems that will be shown in this video comes in all sorts of varieties. So for our first problem, a tank holds 100 gallons of brine solution containing 20 pounds of salt. At time t equal to 0, fresh water is poured into the tank at a rate of 5 gallons per minute, and while perfectly mixed, leaves the tank at the same rate. Find the amount of salt in the tank at any time t.
Now let's consider the given conditions. A tank which holds 100 gallons of solution that contains 20 pounds of salt per 5 gallons of pure water, which means that there is zero amount of salt in the concentration, are added every minute and while perfectly mixed, leaves the tank at the same rate or 5 gallons per minute. Now, let us also put the constantly changing concentration of our output rate. This is over 100 gallon hurlets, use variable S for salt, and divide it by the volume 100 gallons, which remains constant at any time, since the flow rate of both input and output rate is just the same. We also know that the original amount of the salt inside the container is 20 pounds. First, we write down our formula T is over dt equals to IR minus OR. And then we look for the values of our IR and OR. For our IR, there is zero amount of salt for the concentration. Multiplied by the flow rate, 5 gallons per minute is equal to 0. And for the output rate, we have S over 100 gallons for the concentration. Then multiply this by the flow rate, 5 gallons per minute. Its product would be 5S over 100 pounds per minute, or S over 20 pounds per minute in its lowest terms. Now going back to our original formula, D is over dt equals to IR minus OR. And now we have negative S over 20. Writing this down below and then manipulate it further, we have D is over S equals to negative dt over 20. The next step is we integrate the both sides.
Integrating this, we have ln s equals to negative t over 20 plus c.
We use the logarithmic formula for integrating dS over S, and on the other side of the equation, we use basic integration for constant number. To eliminate our ln, we use one of the laws for logarithm, where e raised to ln a equals a. So let's raise both sides as exponents of e. Then we manipulate the equation and arrive in the form of s equals to c e raised to negative t over 20. This is now our general solution. But what's asked in the problem is the amount of salt in the tank at any time t. This means that we need to come up with a function where we could find the amount of salt in the tank at any given time. Since we already know from the problem that at t equals 0 where was 20 pounds of salt, we can use this to find our value for c. We just have to use our general equation and substitute 20 for s and 0 for t. By manipulating this further, we'll find our c being equal to 20. Then going back to our general solution, we substitute 20 for c and finally arrive with an answer which is s equals to 20 e raised to negative t over 20. And that, folks, is our final answer. Let's try another problem.
A mixing tank of 200-gallon capacity is filled with brine solution in which 60 pounds of salt is dissolved. At t is equals to 0, the solution in the tank is drawn off at the rate of 5 gallons per second. The tank is refilled at the same rate with a solution that contains 1/10 pounds of salt per gallon. Find the amount of salt in the tank at any time t. Now, if you're up for a little more challenging question, try to pause this video and try this one.
Did you get it? Well, you might as well keep in touch for the last problem. But before that, here's what we know. A 200-gallon tank filled with brine solution concentrated with 60 pounds of salt. There. Drawn off 5 gallons per second and refilled at the same rate with 1 pound salt per 10 gallon. And for our OR's concentration, let's use S over 200 gallons. We also know that at t is equal to 0, the amount of salt is 60 pounds. Again, we write down our formula and look for the values of IR and OR. There. Multiply each their concentration and flow rate. There. Our IR becomes 0.5 pound per second while our OR becomes S over 40 pounds per second. Now, substituting our IR and OR into the formula, and then we'd have 20 minus S over 40. Sure seems a little bit different from the first one, but still, we follow the same process. We manipulate this and it becomes ds over 20 minus S is equal to dt over 40. The technique for this is putting everything that has S on it on the right side and the rest on the left side. This will make it easier for you to integrate. Again, we use the logarithmic formula to integrate the right side, while on the left side is just our formula. There. Multiply both sides by -1, raise both as exponents of e, manipulate, and voila! It's our general solution. Now, knowing that the original amount of salt, which was already in the tank before mixture, took place was 60 pounds. Let's just substitute for 60 our S and 0 for our T. Manipulate so that we can find the value of C. That's it. There. Substitute to the general solution and then we'd finally come up with an answer. S is equal to 20 plus 40 e raised to negative t over 40. Did you finally get it? Kinda easy, don't you think? Well, wait until we see our last problem.
A nitric acid solution flows at constant rate of 6 liters per minute into a tank that initially held 200 liters of water of a 0.5% nitric acid solution. The solution inside the tank is kept will stir and flows out the tank and at a rate of 8 liters per minute. If the solution entering the tank is 20% nitric acid, determine the volume of nitric acid in the tank after 30 minutes. Well, the percentage of nitric acid in the tank reach 10%.
A tank with 200 liters of water which initially held 0.5% of nitric acid, an input flow rate of 6 liters per minute and 20% concentration, and an output flow rate of 8 liters per minute. Now for our concentration, where unlike the first two problems that we tackled, the flow rate of the input and output rate are not the same. So the volume of the solution inside the container is also changing. In the case, since the amount of solution that flows out is greater than the amount that flows in, the amount of solution inside the container will also continue to decrease. Hence, its concentration will be represented as N, divided by 200 minus the difference of the flow rates manipulated multiplied by time. We simplify this and it becomes 200 minus 2T. And now we have our OR's concentration. We also know that the original amount of the concentration is 0.5% nitric acid. Now we can write our formula, then find the value of IR and OR. Multiplying each of its concentration by its flow rate. And substitute its products to the original formula, and now we have this. Now, take a moment and look at the equation. If you can notice, we could easily manipulate this formula and turn it into the standard form of linear differential equation. Following a process of LDE, we would have our general solution. Next, we substitute 0.5% or 0.005 for N and 0 for T. And then manipulate. Then we'll have the value of RC. Substitute it to the general formula and we have our particular solution. But what asks for the problem is the time that it would take for the amount of the concentration in the tank to reach 10%. We need to remember that the concentration in the tank is the concentration that comes out of it. This means that if we're trying to find the value of T, also need to consider the value and the solution in the particular time. Then we substitute Rn. Manipulate and find the value of T. And that is the answer of our last question.
Aside from the aforementioned real-life examples of a mixture flow problem, we can also witness situations like those in sewage treatment facilities, manufacturing plants, even in cooking.
Differential equations really had a multiple of applications that can be witnessed in our everyday life, and mixture flow problem is just one of them.
Differential equation.
Differential equation.
Differential equation.
Differential equation.
Differential equation.
Differential equations truly have a remarkable ability that shape the world around us.
Alright, that does it for everything.
Thank you for watching!
Big acknowledgement to our Sir Jemer Tamari.
You know what to do!
Di ba, di mo marag, di ka naman sila sit na.
Say something.
Alright, that's all for everything. Thank you for watching.
Di, na ako may bigyan knowledge.
Sige, 1, 2, 3. Alright, that's all for everything.
Thank you for watching!
Ako ba?
Sige na lang, ito na lang.
Big acknowledgement to our Sir Jemmer Tamarik.
You know what to do! Chris lang sapat na.